So this is the first of two lessons looking at solving absolute value equations. The focus of this first lesson will be on solving them graphically, so using graphing technology. The focus of the second lesson will be on solving it algebraically. And ideally, we can, the idea of how to solve an equation like this graphically comes back to us pretty quickly because we did the exact same idea at the beginning of our quadratics chapter on solving quadratic equations. The first lesson of chapter 4 was on solving quadratic equations graphically, and we can exactly apply that idea to this. And so hopefully we can, what sounds familiar is the idea that if I have an equation like this, the absolute value of x minus 3 equals 7, I can graphically plot the function for the left-hand side and plot the function for the right-hand side and see where the two functions intersect. And for that, although I could do this by hand, that's kind of what we did in the last lesson. The idea is I'm going to use graphing technology here. So I'm going to go to Desmos here, and I'm going to graph two functions. I'm going to graph the absolute value of x minus 3, and I'm going to graph just y equals 7. So what you see in blue is the left-hand side of the equation. What you see in green is the right-hand side, and I'm trying to see where these two intersect. And I'm solving for x, so all I really care about is the x-coordinate, which is -4 and 10. Those are my two solutions, -4 and 10. And so my work is right here. My work was graphing using technology. My solutions are -4 and 10. And so for the notes, I just have a sort of sketch of what I just visualized in Desmos. But I'll just label the graph in blue in this case was y equals the absolute value of x minus 3. That was the left-hand side of the equation. And the graph in red was y equals 7. That was the right-hand side of the equation. And again, this idea applies to anything. It doesn't matter what the equation is. If the left and right-hand sides can be graphed, you can solve any equation this way. Hence, it's so important. We don't want to forget about this key idea. And so x equals -4 and 10. All right, so I should be able to go through these fairly quickly as long as we have access to a graphing device. So let's look at this equation. I want to graph, or I want to solve the absolute value of 2x minus 5 equals 5 minus 3x. So again, I'll graph the left and right-hand sides of this equation. This time my right-hand side is not a constant number, it's a linear function itself. But that's OK, I can graph that quickly. There's the left-hand side. There's the right-hand side. And so what I see, especially if I zoom out, is that these two functions intersect in only one spot, right there. And so my solution is 0. Again, I'm solving for x. And so the 5 tells me that these two, the left and right-hand sides, equal each other. Or when x is 0, both sides equal 5. But I'm trying to solve for x, so it's all the 0. It's all I care about. And again, if I zoom out, I can confirm that's the only solution. There's no other solution hiding somewhere. So x equals 0. And so again, I have a visual already kind of set up here. Left-hand side, right-hand side. And there's the one and only solution. All right, so what about this one? At this point, I would encourage you just to pause this and try doing it yourself. I'm hoping this is quite straightforward. I will say for this one, I'm not going to bother going to Desmos because I have it already kind of sketched out right here. But if I graph the left and the right-hand sides, I see this. The left-hand side is what you see in blue, the absolute value of 3x minus 4, all plus 6. And the graph in red is just y equals 3. So these two graphs never intersect. So these two graphs, therefore, tell me that there is no solution. There is no value of x that makes the left and right-hand side equal each other. That said, I'm hoping it's not a crazy idea to realize we actually could have noticed this without graphing anything if we did a little bit of algebraic rearranging to our equation. So although this is great, and here's my answer, I'm done. Let me go back to the start. Notice if, because I have lots of options, if I decided to subtract 6 from both sides, just to have that absolute value expression on the left isolated, I'd have the absolute value of 3x minus 4 on the left-hand side and -3 on the right-hand side. right there I can tell there's no solution. Because there's no way I can find the absolute value of something and have it equal a negative number. It's not possible. And so if we notice that, then we can see right away that, yeah, this has no solutions. That's it. There's always more than one approach. All right, so the last example before a final problem is a quadratic equation inside an absolute value equation. And so for this one, again, graph the left and the right-hand sides. And I'll show this in Desmos again, because this is a little bit different than the previous ones. All right, there's the left-hand side. That's a better view of it. And just equals 1. So I can visualize this already, but there we go. And so this is what the system looks like. And so I can see there's 3 intersection points, 3 solutions. So one's at 1, one's at about 2.414, and one's at about negative 0.414. And so I have 3 solutions. One of them is an exact value. 2 of them are decimal approximations. And that's what I have kind of sketched out right here. So again, I'll label these. And again, I had 3 solutions. So x equals 1 was the most pleasant. I had negative 0.41 approximately and positive 2.41 approximately. So keep in mind, those last 2 I wrote were approximations. Now, if I want to know exactly what the last 2 were, well, then I'd have to solve this algebraically. And we'll get there, well, really soon, actually. But that will take considerably more work than this, which was, again, I did in front of you. It took, the actual graphing part took no time at all. Never, never, never lose sight of the importance of how simple this can be to solve something graphically if we have graphing technology, which we do. All right, so I want to finish things off by leading into the idea about how we can solve these things algebraically. And so I want to solve this equation, the absolute value of x squared minus 4 equals 4, but algebraically. And the one approach are these sort of 4 steps here that I'm going to recommend we follow. So first thing I want to do is just make a quick sketch, just a rough sketch of what the left and right-hand sides would look like, what the absolute value of x squared minus 4 would look like as a function, and what just 4 would look like. And that should give me a rough idea, at least, of how many solutions we'll have. So let's do that. So I'll make a little xy axis here. And so if I want to visualize, this goes back to the last lesson, the absolute value of x squared minus 4, I probably first just want to visualize x squared minus 4. So x squared minus 4 would have a x-axis down at negative 4. It would open up. It would look something like this. Not only that, I know the x-intercepts would be exactly at negative 2 and 2. I know that from just realizing there's no stretch on this graph. So I'd have a point 1 over and 1 up, and then 2 over and 4 up. And since this already is at negative 4, I know that would lead me to my x-intercepts. And what you see here is my rough graph of x squared minus 4. So the absolute value of this would actually go up to positive 4 and look something like this. So there's my graph of the absolute value, my sketch of a graph of the x squared minus 4. And so I know exactly it has a sort of bounced vertex at 4. I know there's x-intercepts at exactly 2 and negative 2. And again, I was able to get those x-intercepts quite quickly because I knew that x squared, from any vertex of x squared, I can find a point by going 2 to the right and 4 up. And that I could just see would bring me straight to the x-axis. All right, so there's the graph of the left-hand side. Well, even easier is the graph of the right-hand side. Y equals 4. Looks like that. So right now, I can tell with certainty there are 3 solutions. I know there's a solution. In fact, I can see one of my solutions. I can see one of my solutions is 0, because I know the vertex goes through 4. And I know there's 2 other solutions, but I don't know where they are. I know one's a little bit less than -2, one's a little bit more than +2, but that's all I can tell so far. All right, so I already have part of my solution, and I know there's 3 solutions. So how can I find all my solutions? Well, next, let's write the equation of the absolute value of x squared minus 4 in piecewise form, which again is not easy, but we have done that before. So let me kind of write that right here. So the absolute value of x squared minus 4. If I write in piecewise form, one piece is just x squared minus 4, and one piece is negative x squared plus 4, where I just kind of change the signs of both. And again, I did that pretty quickly because, well, we've done this sort of stuff more than once. And look at this for top piece when x squared minus 4 is greater than or equal to 0. Look at the bottom piece when x squared minus 4 is less than 0. Well, it's more about those restrictions now. So that top piece of x squared minus 4, I want to isolate x. So when is x squared minus 4 greater than 0? When is this graph of x squared minus 4 greater than 0? Well, I have the first thing I did was sketch out the graph of x squared minus 4. I drew it in blue as a dashed line. And so x squared minus 4 I can see. And so where is x squared minus 4 greater than 0? One of the outputs greater than 0? Anytime we are less than -2 or greater than +2. I can just see it there. And so this restriction is when x is less than or equal to -2 or x is greater than or equal to +2. And so the other piece, negative x squared minus 4, or sorry, plus 4, I can just tell from looking at the graph, that's when, again, looking at this part here, that's when x squared minus 4 is less than 0, which I can see is this region right here. So between -2 and 2. All right, so now that I have my equation in piecewise form, as it says here, I should have 2 similar, or different, but similar equations, and I do. I have x squared minus 4 and minus x squared plus 4. They're similar, but they are different. And now I can use these to solve for where this equation equals, where the equation equals 4. And so I can look at each of these pieces and make them both equal 4. So for example, if I look at the top piece, I can make x squared minus 4 equal 4 and solve that, which really quickly I get to x squared equals 0, which means x equals 0. And that's the answer I knew about already. But, hold on to your hats. What did I do wrong here? Sorry, I have some sort of mistake here. Ah, yes. The reason I knew I made a mistake is that I have a solution. I mean, I will say x equals 0 is one of my solutions, but I came around it the wrong way. And the reason I knew I made a mistake is that I only look at this piece, I'm only supposed to look at this top piece when x is less than -2 or greater than 2. So 0 is not part of that restriction. Yet I know 0 is an answer. That's how I knew I made a mistake somewhere. And I'm hoping you already saw the mistake. The mistake was up here. Classic mistake by just doing things a little too quickly. I should have added 4 to both sides here. Right? If I subtract 4 from both sides, that doesn't do me any good. So I get x squared equals 8. There we go. And so when I isolate x, I get the square root of 8, or actually plus or minus the square root of 8. And now these solutions here, if I look at these, I just got to be careful and make sure that these solutions are actually part of my restriction up here, because I'm only supposed to look at this equation when x is less than -2 or greater than 2. So is root 8 more than 2? And yes, it is. How do I know the square root of 8 is more than 2? Well, I know the square root of 2 is 4. And so the square root of 8 must be more than 2. I know actually the square root of 8 must be close to 3 because the square root of 9 is exactly 3. So I know that these two solutions I found here, plus or minus root 8, are part of my restriction. They fit that piece. And so now I know that those are the exact two answers for these 2 points up here. I know these points up here, one is root 8, one is minus root 8. With that said, the other equation, which I don't really need to work with because I've already found the other answer graphically, but I'll be consistent and I'll use it, is I now take that equation, negative x squared plus 4, and make that equal to 4. And this time I subtract 4 from both sides, so get negative x squared equals 0, which means x squared equals 0. You can divide both sides by negative 1, or negative 1 if you want, or multiply both sides by negative 1, which means x squared equals 0. There's that answer of 0 that I knew we'd get. I just came up with it in the wrong spot before. And again, double check. I got an answer of x equals 0. Does that fit that restriction right there? Yep, because I only pay attention to this piece when x is between negative 2 and 2, and 0 is most definitely in between negative 2 and 2. So now I've algebraically solved this equation. There are 3 solutions, plus or minus root 8 and 0. Notice, although I got some exact solutions, I think that was more challenging than just solving it graphically, because it required a whole bunch of things. Going back to quadratics, understanding absolute value functions, understanding piecewise form. Again, absolute value is deceivingly challenging, even though in its essence it can be something quite simple. Just make it positive. But start connecting it to equations, and it can get, surprisingly challenging. And this will be kind of the focus of our next lesson.